Hey everybody, in this video we're going to talk about Simpson's rule. And so what is Simpson's rule? Before we talk about it, I want to talk about where we've come from. So way before, when we started talking about area under a curve, we did Riemann sums, and we learned how to find the area under a curve by using rectangles to approximate it, and eventually we took the limit as the number of rectangles went to infinity to give us the exact area under the curve. So if you remember, and happy St. Patrick's Day, when we did this, we used left endpoints, divided our interval from a to b into equal length pieces, delta x b minus a over n. And then we use left endpoints to find the area of our region. And then we use right endpoints, and usually the left endpoint was an over approximation, depending what the curve looks like though. The right endpoint in this case looks like it will be an under approximation. And then we also had the midpoint. The midpoint was probably our least favorite because we had to find not only delta x, but then the midpoint of all those little x of i's here. And the midpoint gave us the height. And then earlier I showed you the trapezoid rule. So with the trapezoid, all of our little delta x's, we use trapezoids to approximate the area under the curve. So what does Simpson's rule use? So Simpson's rule uses parabolas to approximate the area under the curve. So if I have the same function, some function from a to b, so we're still gonna chop it up into equal pieces. But to make this a little more intentional, let me say we're gonna use 4 parabolas. So if I break it up into 4 equal pieces, then what Simpson's rule does, it tries to fit a parabola, the best fit parabola, on those intervals to approximate the curve. So how many points are needed to get the equation of a parabola? Each parabola needs 3 points. So when n equals 4 for 4 intervals, I'm really using 2 parabolas. So notice that I'm going to be using a parabola that covers these 3 points, and then a parabola that covers these 3 points. So that's how Simpson's rule works. So instead of using nice geometric shapes that we know, like rectangles and trapezoids, it's going to try to really fit the curve the best that it can with a parabola. And for a parabola, we need 3 points, so 2 parabolas fit in 4 equal pieces, right? We have a delta x there, a delta x there, delta x, and delta x. We have 4 equal pieces to give us 2 parabolas. What this also means then is that for Simpson's rule, what kind of n am I going to need? Could I do this if n was 3 or 5? I can't, right? Because I won't be able to fit 3 points. If I had 5, I won't be able to use 2 of the points, so it comes out odd. So for Simpson's rule, n has to be even. Alright, so how does Simpson's rule then work? Well, for any parabola, the equation of a standard parabola is ax squared plus bx plus c. I'm not going to use a and b because I've used them there. So let's think of something else I can use. Well, I guess I can still use a, but I'm going to say a2x squared plus a1x plus a0 to sort of match the degree. And if I wanted to do the area under that, from regular A to B, notice I'm not going to go into too much detail of Simpson's rule, but when you see the formula, I just want you to know where the 1/3 comes from. So this will be a2x cubed over 3 plus a1x squared over 2 plus a naught x, and so on. You evaluate it from A to B. And then we're going to have another parabola, so b2x squared plus, but all of these parabolas, after you integrate them, they're going to have this common 1/3. So the formula for Simpson's rule is that the area is approximately 1/3 that 1/3 when you integrate times delta x, and then we're going to do times f of your first endpoint, so f of a, usually that's your x1, and then you're going to go from there slightly different, so it's going to be plus 4 f of x2 plus 2 f of x3 plus 4 f of x4 plus 2 f of x5, and so on and so forth, plus 4 f of x of n minus 1 plus f of x of n. And that is Simpson's rule. So you have n has to be even, and essentially so that this kind of 4-2-4-2 pattern works out. And again, I don't want to go into too much detail as to where it comes from, but I'm sure you can look it up in the appendix of the book, or there's probably some other YouTube video you can find out the derivation of Simpson's rule. But essentially, once you integrate a parabola and another parabola, notice how the same points are used. So that point, and I can use that one with another one, and so some of these points get used multiple times. So that's where this is coming from. So let's try to do it for our same example as before. The integral from 1 to 3 of 1 over x dx using Simpson's rule with n equals 4. Remember from our trapezoid video, the function is 1 over x. Break it up into 4 equal pieces. We have 1, 2, 3. So what was it? 2, it was 3 halves and 5 halves. So those were our same endpoints from before, or interval points. So according to the formula, delta x is b minus a over n, so we still get 3 minus 1 over 4, which is 1/2. And with Simpson's rule, this is going to be approximately 1/3 times delta x. Delta x is 1/2 times f of 1, right, our first endpoint, or our first point here, plus 4 f of 3 halves plus 2 f of 2 plus 4 f of 5 halves, and the last one is the single one, so plus f of 3. So here I'm going to have 1/6 times f of 1, we know is 1 over 1, plus 4 f of 3 halves. Remember, our function is 1 over x, so f of 3 halves is 1 over 3 halves, which just gives us the reciprocal, 2/3. So times 2/3 plus 2 f of 2 is the reciprocal of 2, so 1/2 plus 4 times the reciprocal of 5/2, which is 2/5. And f of 3 is the reciprocal of 3, which is 1/3. And when you do all of these out, I got, this is approximately 1.1000. Now, when we did it with the trapezoid rule, we got 1.1167, and we wanted to know what was the error. So here we get 1.1000. So same thing. What is the error? And if you remember our actual, so the error, the absolute error is the actual minus the approximation, which in this case, our actual was, when we did the integral, 1.0986, and in this, for the Simpson's rule, our approximation is 1.1000. So this gives us 0.0014. So it seems to be a better approximation than with the trapezoid rule. Remember, the trapezoid rule, the error was 0.0181. So this one, we are a lot closer with Simpson's rule. So that's one of the reasons that this works really nicely. The error in the Simpson's rule, right? Remember, this is if we know the actual, but most of the time the reason we're using this rule is because we don't know the actual. So the formula for the estimate error using the Simpson's rule is that the actual error has to be less than or equal to b minus a to the 5th over 180 n to the 4th. I know there are many questions. Why? Where does that come from? These formulas have very intense mathematics that go behind them, so just take my word for it. The maximum of, you're not going to like me for this, the 4th derivative of the original function for a less than or equal to x less than or equal to b. For the Simpson's rule, for the trapezoid rule, it was the absolute value of the 2nd derivative. In this case, we need to go to the 4th derivative. So, back to our original, it was 1 over x dx from 1 to 3. So we know, again, we know a, b, n, and we know f of x. So in the formula, so far, we're going to have for 1 less than or equal to x less than or equal to 3, right? That's the, or a less than x less than b. The actual error is less than or equal to b minus a, so 3 minus 1 to the 5th over 180, n is 4. We're using 4 partitions to the 4th. Kind of lost track of that. And now the maximum of the absolute value of the 4th derivative. Whew. So we have to find this. The maximum of the absolute value, don't forget about taking the absolute value of the 4th derivative. So we know that f of x is 1 over x. So its first derivative is minus 1x to the minus 2. Second derivative, 2x to the minus 3. For Simpson's rule, we would have, for trapezoid rule, we would have stopped right there. But for Simpson's rule, we need to go further. So this will be minus 6x to the minus 4. And finally, the 4th derivative is 24x to the minus 5. which is 24 over x to the fifth. And now we need to figure out when does this have a max? So when is this the largest? On 1, 3. And again, you can do by analyzing it. We could do by using Calc 1 methods, which means I will take, we need to find the absolute value. Well, the absolute value will be the same thing because on 1 to 3, x to the fifth is positive. So the absolute value of a positive will stay positive. So this is positive, and notice that as the interval moves to the right from 1 to 3, this is going to get smaller, right? The bigger the denominator, the smaller the fraction. So this is going to have maximum at 1. And what is the maximum? The maximum will be 24 over 1, which is 24. So that's the max. You could also do the derivative of this, right? Call it something else, call it g. And now that's your function that you want to find the maximum. So take the derivative, find critical numbers, and find the absolute max and min on that interval. Or you could also graph it on a graphing calculator and then see on interval 1 to 3 where does the max occur. But back to our error. So I know the error in Simpson's rule, the actual error has to be less than the estimate error. So 3 minus 1 is 2. So I'm going to have 2 to the fifth, which is 32, divided by 180, and to the fourth, which is 4 to the fourth, times the maximum, which is 24. When you do this on a calculator, we end up with 0.0167 is what I got. And with the trapezoid rule, what had we gotten? We can look at our previous notes, and it was 0.0833, so this is much better. Remember, the actual error was, well, in this case, we have our actual error up here, which is 0.0014. So the actual error, 0.0014, is it less than or equal to 0.0167? And yes, it is. So that this is true. So we're good. But again, we're most of the time not going to know this value, but we know that the actual error is going to be less than the estimate error. So as long as this is small, you're going to know that that's going to be even smaller. So that is Simpson's rule. So the formula to know for Simpson's rule is what I wrote in the previous page. So this is your Simpson's rule formula. Alright, and I would encourage you to do a problem on your own. You can try on your own the same one from trapezoid rule. So the integral was from 0 to pi of sine x dx with n equals 4 using Simpson's rule. Now the thing to keep in mind here is that when we say n equals 4, it doesn't mean 4 parabolas, but that you're going to break up your interval into 4 equal pieces. Alright, so try that, and I will post a solution to the trapezoid exercise for this and Simpson's rule exercise for this.